All right, so now let's look at motion. Motion both for input and for output. And there's actually quite a number of ways we can do that. So first of all, let's have a look at how we can use motion as an input, and specifically the motion of the device itself. For this, we need the so-called IMU. Just about any phone has an IMU built in. If you have a really cheap phone, then it sometimes only contains the accelerometer. This is something that you can just assume that any smartphone will have. And the accelerometer is designed to measure acceleration. That's quite obvious. The important part is it also measures gravity. Gravity is also a form of acceleration because it's, of course, pulling things towards the surface of the Earth. And so the gravity, the always present acceleration due to gravity, will also be sensed by the accelerometer, and that can help you figure out the orientation of the phone. So at the most straightforward use case is that it will simply detect if you're holding your phone upright or if you're tilting it to the right. It cannot detect when you rotate your phone around the axis that's pointing downwards, because the acceleration vectors will just not change in this case. For that reason, most IMUs, except the really cheap ones, also contain a compass or magnetometer that's measuring the magnetic field in the environment, and they contain a gyroscope that measures rate of turn. So if you turn your device across, along the gravity axis, then the acceleration sensor will not sense that motion, but the gyroscope will, because it measures rate of turn. And also the magnetic field will also change. However, the magnetic field is a little less reliable usually, because things like steel mesh in the walls or even just the steel legs on furniture can get magnetized. Things like cars, when you're walking outside, cars can also be magnetized because they're, of course, just made of steel and metal. And these things can actually distort the magnetic field quite a bit. And for that reason, the magnetic field measurement in your mobile device isn't used quite as often. Or it's just used as a secondary input for figuring out the overall orientation of your device. So we have, in general, we have 9 measurements. So 3 acceleration axes, 3 rotation axes, and 3 magnetic field axes. And these 9 measurements are put into sometimes quite complex sensor fusion algorithms. And these are fused together to form 3 degrees of freedom absolute orientation of your device in space. This is only the orientation. This is not the position. So if I put my device on the floor horizontally or on the table horizontally, will not make a difference to the IMU, because the orientation from the point of view of the IMU is exactly the same. I need some other additional sensor like GPS or camera or so to actually create a so-called pose with 6 degrees of freedom that gives me both the position along 3 axes and the orientation along 3 axes. If I have a known starting point, then I can up to a certain point, use the data from the IMU to also estimate the change in position, but only the change, not the absolute position. So if I have my phone on the table, for example, and move it up 20 centimeters, or if I have it on the ground and move it up 20 centimeters, then again, this will look exactly the same to the IMU. And in addition, the data from the IMU is quite noisy, and especially if I use it to estimate the position of my device, then these errors will very quickly accumulate over time, and so I can only use this for relatively short stretches of time before the errors just become too large. And in many cases, when I run all these sensors together, then they will actually consume a noticeable amount of power. And to counter that, usually only the acceleration sensor is actually running when it's not being used specifically at a low rate to just detect the change in orientation of the device. So for that reason, there's also usually a very slight delay when you turn your device until the screen actually reacts to that. So how do these sensors actually work? So now I'd like to go a bit more into the technical details. These IMUs usually are constructed as so-called micro electromechanical systems. And this means that we have miniature mechanical objects, things like springs and weights and actuators and so on, that are etched directly into silicon like an integrated circuit. So you can basically manufacture it all in one go, both the actual readout and sensor fusion electronics and the sensor itself. So here you can see an example of such a MEMS accelerometer, and if you look closely, then you will see that these structures in the corners are actually springs, and the structure in the center is more or less a weight. And so if the device is accelerated, let's say upwards, then this weight in the center will shift downwards a little, just because of inertia. And built into these brackets at the sides of the weight are electrostatic sensors or capacitive sensors actually that can measure the distance between the brackets and the weight. And when it's shifted because of acceleration, then the distance will also change to those brackets, and that can be measured and mapped into an actual acceleration value. The kind of limitation of this approach is that, of course, these tiny springs have some specific stiffness, and there's also only a limited amount of movement range for this weight in the center. So these factors together limit the range that you can sense. Usually these accelerometers have a range of somewhere between 2 and 8 G. So 2 to 8 times the acceleration due to gravity. 8 G is actually quite a lot already, so therefore to exceed that you would have to move your phone quite fast. To sense rotation and magnetic field, we also use these MEMS systems. So for rotation, usually we use a so-called vibrating structure gyroscope. So there we have two weights that are connected by a spring and that are put into vibration. Again, this is microscopic scale, so these are a few micrometers large, only these weights, but they can still be made to vibrate, again with electric currents, for example. And when you now turn the entire system across this, along this axis, then the weights will displace each other due to the Coriolis force. That's kind of very small detour into physics. That's the same thing that causes the water in your drain to spiral. That's also the Coriolis force. And the same effect can then be used to measure how much these vibrating weights are displaced, and that in turn can tell you something about the rate of rotation of the object. And last but not least, for the magnetic field, the so-called Hall effect is used. So we have a plate in the center here that's conducting current in this direction. And when you apply a magnetic field, then maybe you still remember this right-hand rule from physics class, then the electrons will be deflected to one side, and that will induce a voltage across that plate that can again be measured to find out the strength of the magnetic field. One thing to watch out for in this case is that this Hall effect sensor is actually very sensitive to any sort of stray magnetic field, both from the environment, but also from the device itself. So, for example, the power supply in a mobile device can actually draw quite a bit of current from the battery, and that current then again creates a magnetic field. And so when you design such a device, then you have to take special care that the magnetic field sensor is as far away as possible from the power supply lines, for example. Yeah, so this is something to watch out for. I already mentioned that there's also these issues in the environment, like a overhead power line, for example, or a car that's kind of magnetized that can also distort the magnetic field in the environment. And so sometimes you might have noticed that when you have an app that's, for example, tries to use the compass actually. So one example is this the sky map thing from Google that allows you to look for constellations and planets in the sky. And this app often asks you before you actually start the app to do a calibration by doing an H-shaped movement with your device in air. And the idea of this H-shaped movement is that your phone will pass through as large number of different orientations as possible in the same space, and that will allow the device to figure out the kind of the magnetic field strength overall in this environment, independent of the angle, because the magnetic field of the Earth is in theory supposed to be angle independent, except if you're very close to the pole. In other parts of the Earth, it's more or less parallel to the surface of the Earth and also has a constant strength. And if you do this figure 8 calibration, then you should be able, or the sensor fusion algorithm should be able to remove as much as possible of stray magnetic field from the environment around you and just filter out the magnetic field that's actually from the Earth itself, and then use that to actually get an accurate direction again, even if you're inside an unpredictable environment, which has, like, if you're in a building, steel mesh in the walls, and so on. All right, so much for how to actually sense motion. Now let's have a look at how to use that. One thing that's come up recently for various use cases, so for example for virtual reality or for also editing, augmented reality and so on, are these handheld controllers that you can also use to input data into a mobile device. So there's quite a number of different flavors, like this Daydream, for example, or this Litho. What they all have in common is that they usually have some kind of combination of buttons, a touchpad, of course an IMU to actually sense orientation in space, and Bluetooth Low Energy to communicate with the device. Not something that's widely used, maybe except for, if you're generous, then you could count something like a selfie stick among these two, because it's also kind of an add-on controller. Sometimes they even have motion sensing built in, but apart from that, it's again kind of a niche way of inputting data for a specific type of use case. So much for motion.